Okay, let's get this show on the road. Hello, everyone. Hope you're well. Welcome to another edition of Math 1207. We're starting a little late, so let's jump into it. Make sure I can see the chat. Okay. Let me make sure. Disconnect my phone from my headphones because otherwise it might disturb me. Okay, all right. I think we're good. Okay. Hopefully you guys are okay. Had a good day, had a good weekend. Time to jump back into it. We are solidly in phase 3 of the class now. The last two phases of the class are going to be very short, very small. And as I mentioned, they're starting from the basics. So it actually shouldn't be tough. The last month-ish now, I think our last class is around the 8th or the 7th or something like that. So we have a little bit less than a month left. But compared to the beginning, it's going to be a lot more manageable, I feel. So you now have the chance to catch up on what was going before, as well as maybe also keep up with what's going on right now. So let's jump into it. Since we're off to a late start, let's get into this stuff while our brains are still fresh. We started talking about parametric curves and parametric equations last time. And basically the idea is sometimes you have dependent as well as independent variables, but you want to think of everyone as a dependent variable. So you want to think of each of your variables as functions of some other variable that you can, let me let someone in here. Some other variable that you can track. And this variable is called the parameter. And when you actually write each function, each variable in terms of that new variable, the parameter, we call these parametric equations. And we saw that we could plot them and do all sorts of things with them. So when you don't have parametric equations, you say you have scalar equations. That's what they're called. However, when you want to think of each variable as a function in its own right, you can come up with parametric equations. Trigonometry was born because of that idea. So there are definitions here. Now, when you go from a scalar form to a parametric form, you say you have parametrized the curve. So it is possible to parameterize curves as well. And we also did that. Right, so I spoke about parameterizing circles. So you have an equation like this. You can actually transform it into a parametric set of equations like that, and so on and so forth. The benefit of parametric equations are many, most of which you are going to notice after this class. One thing is that now our curves will also have a sense of direction to them, and that's useful for a lot of context. But there are many other benefits as well, and we will actually start to see some later on today. So we spoke about parameterizing circles and different parts of the circle, and we realized that whereas in the scalar form, these guys would have to be described in a little bit more technical ways. In parametric form, the only thing that happens was we actually changed the limits of our parameter. And that actually, everything else remained the same. So that's one way in which you can already see how this is beneficial. Whereas for this curve, I would probably think of it as y equals the square root of 4 minus x squared. And this curve, it's better to think of it as x equals the square root of 4 minus y squared. Like I have to completely change how I'm describing it in the scalar universe. But in the parametric universe, the only thing I changed was the limits on the parameter, right? So a lot of things you can really affect a lot of change with minimal effort. We also saw that we could parameterize things in multiple ways. And so I parameterized the upper semicircle in 2 ways. There are an infinite number of ways to parameterize any given curve. In this example, you'll notice that the way I parameterized it, we actually go clockwise. However, so notice that this would go around clockwise. if I wanted something like counterclockwise, and this is something you're going to explore more in, I want to say multi-2. I could actually just change to clockwise. I could actually change, so this was going around it clockwise. If you actually plug in t equals -2, you'll notice that you start on the left, and as t increases to 2, you move to the right. If I wanted to actually switch this, I could actually change that just by putting a negative sign in front of t. Now, in terms of reversing orientations with negative signs and when and how to do this, that's something you will cover in multi-2, maybe multi-1, but I think multi-2 is when you're going to talk about something like that a lot, when orientation really starts to matter. So now we're going to jump into the rest of the topics here, and I left you guys with the notes. I did add a few more notes just to some definitions, but it's not going to be a big deal, I think. So let's actually just run through this. So I showed you a standard way to parameterize a circle. It turns out that we have standard ways to parameterize line segments as well. And this is something, again, that in multi-1, they might express this a little bit differently. In multi-1, let me not even write it down. But here I'm taking things component-wise. And essentially, if I want to go from a coordinate x1 comma y1 to x2 comma y2, this set of parametric equations will work. It's for the x, it's x1 plus x2 minus x1 times t. The y becomes y1 plus y2 minus y1 times t. Notice that x1 is the initial x value. You can also think of x2 minus x1 as the difference between the final and initial point, and then you attach a t to that difference. And then you let t goes from 0 to 1. So there, again, there are multiple ways to parameterize anything, and there are ways to parameterize lines where the t does not go from 0 to 1. But for the standard parameterization, doing it this way, your t is always 0 to 1 for this formula. And so I really want to emphasize there that's for this formula, which is usually the formula you're going to want to go with when you want to parameterize straight lines. There's another way you can think about this. You can think of it as x starts at x1. Then you have to figure out, what do I need to add or subtract to get to x2? And then you multiply that number by t. Okay, so we're going to do some examples. This also works in 3 dimensions, as you can see here, with an x, y, and z coordinate. We will actually talk about that in a little bit, so don't worry about that for now. But you could actually do it in 3 dimensions as well. And it extends very naturally to higher dimensions. You could do it for n dimensions. Now, if you allow your t to go from minus infinity to infinity, that will actually trace out the entire line, not just a line segment. A line segment is just a finite part of a line, a part of a line that's of finite length, but you could go in both ways as well. So for the picture for this one would be something like, okay, it starts at, probably don't want to put it in there. So there's a coordinate here, which is x1 comma y1, and there's another coordinate here, which is x2 comma y2, and you want to actually travel along a straight line from one point to the other. This is the form that gets it to you. And of course, you could do this in 3 dimensions. Don't worry about this. We'll talk about it later a little bit. So this is x, y, z, and you can have a coordinate over here, which is your x1 comma y1 comma z1, and there's another coordinate over here, which is your x2 comma y2 comma z2, and you want to travel along a straight line from this point to that point. The parametric equations for such a curve, it's a straight line in this case, but the technical definition, we'd call it a curve, would be what's in the box right here, and it extends very naturally. And essentially, if we allow t to go from negative infinity to infinity, basically, it's like you have the entire line but it also does pass through x1, y1. And x2, y2. So if you know 2 points that you want to pass through, then it turns out that this point, this part of the line, this is the part that's given by t goes from 0 to 1. But if t extends further, you'll continue over here is where t is greater than 1, and over here is where t is less than 0. Okay, so that's basically it. So these are just standard ways. And as you can see, if you look at these equations a little more carefully, if you plug in t equals 0, notice that your x and y is equal to x1, y1 respectively, which gives you the first coordinate. If you plug in t equals 1, then the x would become x1 plus x2 minus x1. The x1s cancel, so your x becomes x2. And a similar thing will happen to the y. So when t equals 1, your x and y are equal to x2 and y2 respectively. So that's why this actually works. You can actually look at that. That would be the right formula. So for example, let's say I wanted to parameterize the line segment from this point to that point. So I have, and you don't have to actually draw this, but I'm just going to draw it because, you know, because I can. So I'm at, say, 1 comma minus 2. So I'm at this point here. And I want to move to 3 comma 4. And then there's just a straight line like that. Okay. Now, how can I write parametric equations like for that? As I mentioned, so you're going to start with the x. Now, you could remember these formulas, and you should remember these formulas, but there's actually a very intuitive way to fill it out. And so to actually get to that, what you can do is just listen to how I'm saying it while I'm doing it. Okay, so I want to parameterize this line segment. So what do? My x starts at 1, so I write down the starting point. Then I ask myself, what do I need to add or subtract to get to the second point? Okay, so my x needs to go from 1 to 3. So if I've started at 1, what do I need to add to get to 3? Well, I need to add 2. And then attach a t to that 2. Right? So it's going to be the initial point plus the difference between the final point and the initial point times t. But you can think of it in your head as, okay, if I'm at 1, what do I need to add to get to 3? Similarly for the y, you start off with a negative 2 in the initial point, and then you ask yourself, well, if I'm at negative 2, what do I need to add or subtract to get to 4? And of course, the answer is 6. And then you let t go from 0 to 1, and you're done. So that is the parametric version of this line. And I already showed you how you would convert this to the scalar version if you so desired. Any questions on that?
No.
Okay, awesome. So I'm not alone. Thanks for letting me know that. And again, cameras on is encouraged. If you're at all comfortable, that would be much appreciated. Now, you can parameterize almost anything else. There are many techniques to parameterize curves. This is the last one we will discuss, though. And honestly, you probably don't need to know anything else, but these are the most powerful ones, actually. knowing how to parameterize circles, straight lines, and using this technique for almost anything else, you can get pretty far doing that. In fact, when I was a little Jhevon going through undergrad, and I was doing a class like Multi-2, I never found a reason to use anything but this in the class. However, with certain homework problems, they got a little bit more sophisticated. And so I can't guarantee that your professor that you would have in multi is not going to want some sort of more exotic parameterizations. But for all the standard applications, these three techniques, knowing how to do straight lines, knowing how to do circles, and knowing how to do anything else with this technique, you can parameterize most things that you'll encounter. This technique is actually one that we have. I did it with you last time, even though I didn't say that I was doing it, but basically it is the technique that I did here, right? Basically, you let one of the variables that are already there be your parameter. And it turns out not all the time is this going to be, it's not always going to set out that it is that way, but sometimes you can just say that. I am going to set this variable equal to the parameter, and then you write all other variables in terms of that parameter, and then you can track the parameter by that variable. So for example, let's say I want to parameterize the part of y equals x squared from the point 0, 0 to the point 2, 4, right? So y equals x squared. Obviously, that's a parabola. But I want to go from the point 0, 0, which is here, and go up to the point 2, 4, which is here. So I want this part of the curve here. I want to parameterize this part of the curve. Now, I didn't say specifically what direction I wanted to move into. It's not always going to matter, but if it does matter, you'd be able to fix it. So that's the part of the curve that I want to parameterize. So now you might say, well, y equals x squared, that's not a circle, that's not a straight line. What is the formula for it? So whenever you have a weird curve where there is no nice formula for it, you can let one of the variables themselves be the parameter. So what I could do here is just set x equals t, and notice that that would immediately give you that y equals t squared because x is t squared. And then what are the limits that I would use here? Well, I would use 0 to 2. And you might ask me, why would you use 0 to 2? Well, t equals x. So the x limits are the t limits. And that's basically it. So that's just a very simple example to illustrate the point. Notice that I could have done this alternatively. And it's not always, this isn't always convenient, but in this case, it's very, it's convenient enough. Notice here, alternatively, I could have set y equals t. This would mean that my x would be the square root of t, right? I know I want to take the positive. For the right side. And then I would just set t. Now my t is following the y values. So what would my t be for this parameterization?
Zero to 4.
0 to 4. Right? So we could do x equals t, y equals t squared. T goes from 0 to 2. Or we could do something like y equals t, x equals the square root of t. T goes from 0 to 4. Those guys both trace out the same curve. In fact, they actually go in the same direction. They both go from the origin to the top, right? So you just pretty much set someone equal, and you can make this a little bit more sophisticated. I don't know if I do want to do that though. Let's keep it simple. I was going to give you this another example, but whatever. Let's not do that. Yeah, you'll see examples like that in multi-1. Let's not push things too much. Now, of course, we are in a calculus class, so that's what I told you is the basic of parametric curves, right? You should know what it means to create a parametric curve. You should know how to go between a scalar and a parametric curve. You should know basically how to sketch them as well, and how to parameterize certain situations. But we are in a calculus class, so doing calculus with parametric curves is obviously going to be of interest. So you might wonder, okay, so if I was a scalar equation, y equals f of x, and then suddenly I change things to parametric equations, what if I want to do something like find a derivative, find the slope of the tangent line like we're used to? Do I have to go back to the scalar version to do this? And the answer is no. And the reason why the answer is no is that we can use the chain rule. The chain rule is a very useful rule. It's not even funny. A lot of rules in Calc 1 were derived using the chain rule. Maybe your professor did it with you, but I'm not sure. But a lot of things in the future are going to be derived using the chain rule, including this rule here. It turns out we can figure out how to find dy dx for a parametric curve in terms of the variables of the parameter. So how would you do that? Well, one version of the chain rule is this. It's not the version that most people remember, but it is a version. Most people would remember this part as being f of g of x, and this part here is the g prime of x. So this is equivalent to f of g of x prime equals this, right? So most students will know the chain rule in that formulation, but it's the same as me writing this, dy du versus, so this is the same as saying something like df dg times dg dx, right? And so I can actually use this to my advantage. Basically, if I see dy dx, I can think of this as dy dt times dt dx by the chain rule. And so now, just rearranging, I can think of this as dy dt divided by dx dt. In other words, dy dx is the same as y prime of t over x prime of t. Maybe I didn't put that in a box. I didn't type that on a box, so let me actually write it out. So dy dx, I can think of it as dy dt over dx dt, where t is a parameter. If x equals x of t, y equals y of t. Similarly, with the Leibniz notation is very nice this way. You can actually play around the Leibniz notation almost as if it were a regular fraction. So I could think of the dt dx, I can think of it as 1 over its reciprocal, and I get the dy dx dt. So it's very nice. The Leibniz notation is very convenient that way. And it's more convenient than you might realize, because for the second derivative, you would play a similar game. You would think of this as, well, this just means d dx of the first derivative, right? The second derivative is the derivative of the first derivative. Now I already know how to find dy dx, right? So we'd find this by doing that. But we're going to maneuver it by actually multiplying and dividing by differentials. Notice that I can think of this as the following. So I can divide the top and bottom by dt. Which, it's weird that you can do that and that works, but it actually works. The Leibniz notation is really nice that way. And so, yeah, a lot of people think that Newton, of course, there was controversy versus did Newton invent calculus or did Leibniz invent calculus? Did one person steal from the other? It turns out that the way Leibniz developed calculus was actually a lot more user-friendly than Newton's way. So it turns out there are a lot of things that if you're using the prime notation and Newton's conceptualization of calculus, to prove things, it's very difficult. Whereas with Leibniz, the way he set up his notation for the derivative, it's like you can treat it like a fraction. You can multiply and divide by a differential, and it's like it all works out. So it was really nice. So you can actually do that. Rearranging a little bit, this basically says d dt of dy dx. And again, remember, my dy dx would be a function of t in this instance, and then I divide by dx dt. So that tells you how you'd find the second derivative. You take the derivative with respect to t of the first derivative, and then you divide again by the derivative of x. And of course, derivative exists. You're not dividing by 0 or anything weird like that. And that's it. You just you need to remember those formulas, right? So it's probably easy enough for you to derive this every time you need it, but it's worth just memorizing it. Just like how you memorize the quotient rule back in Calc 1. These are just some new rules for you to memorize. You just memorize them and follow them. I'm not going to ask you to prove this at any point, and I don't think anyone after this will ask you to prove it. Of course, there are some things that should follow right away. Of course, looking at the derivative equation, notice that if your dy dt equals 0, you have a horizontal tangent line because that means dy dx equals 0, provided that you're not dividing by 0 at the same time, right? So if your dy dt equals 0 while your dx dt is non-zero, you get a horizontal tangent line. Vertical tangent lines, it happens when the slope is undefined. So that would occur if your dx dt is 0 and your dy dt is not 0 at the same time. Now, if both your dx dt and your dy dt is 0, then you end up in a 0 over 0 case, which is indeterminate. And if you want to look at such a point, you would usually do it via L'Hopital's rule or something like that. So if you realize the derivative as at t equals a gives you 0 over 0, what you would do is you would take the limit as t approaches a of dy dt divided by dx dt, do what you can do with L'Hopital's rule or rewriting the indeterminate form, right? You would apply L'Hopital's rule, hopefully it works out, and then you can conclude from that. But if both the top and bottom go to 0, you do not know in the beginning what's going to happen. However, it's very clear. If the top is 0 and the bottom is non-zero, you have a horizontal tangent line. If the bottom is 0 and the top is non-zero, you have a vertical tangent line, slope is undefined. If both go to 0 at the same point, use L'Hopital's rule, or just consider it as an indeterminate form and do what you need to do to get the limit to work. So conceptually, that shouldn't be strange to you. That's a very Calc 1 concept. Slope equals 0, horizontal tangent line. Okay. Now here, I X this out because I didn't really want you guys wasting time on it, not because it's not important or I wouldn't expect you to know how to do this, but again, it's a very Calc 1 kind of thing. So I'm not going to do this example in class. So I should really just say do on your own. And I think there are a couple of examples of this in your homework. But again, once you find your dy dx, you know you can find the slope of a tangent line using the derivative, and then you just y minus y1 equals m times x minus x1, plug in the points, and that's your tangent line. So again, very Calc 1 thing, so I'm not really going to do that. But because the new part of this is these formulas, so I will do the first two examples. By the way, this is the parametric curve. It's a picture just for fun. I was going to draw the tangent line on this. So when t equals -2, it would have given you a certain point, but whatever. And I would be able to sketch the tangent line on this. But this is what the curve actually looks like. So when my x is a quadratic and my y is a cubic, notice that something very interesting can happen. It's a loop-de-loop. Here's another very important thing. Note, this is not a function. It fails the vertical line test. However, we can examine it as a pair of functions via parametric equations. Okay. So I'm kind of just subtly dropping hints towards why this topic is even important. Why are we even talking about it? It really, really can help, right? So there are some things that are very complicated to deal with because they're not even a function. So everything you knew about functions and what you could do with functions, you couldn't really do it with this curve. However, in parametric form, I am dealing with two functions. My x is a quadratic and my y is a cubic, and I know how to deal with those individually very well. So sometimes it's actually to your benefit to, even if you have a scalar version of a curve, you'd want to transform it to a parametric version of the curve because there's a lot of machinery and functionality you can have by doing that as opposed to not. Okay, so let's actually, so I'm going to do parts A and B for you. And again, I think this is so overall, this is straightforward if you remember the formula. So I think I can just go through it and you can watch me. So I want to find dy dx. This is the first derivative of this parametric curve. So I'm just going to remember the formula and I'm going to write it down every time so that I remember it eventually. Dy dx just means y prime of t over x prime of t. So I'm going to differentiate my y function, which is 3t squared minus 3, divided by the derivative of the x function, which is 2t minus 1. And that's it. This is my dy dx in terms of t. So I don't need to go back to the xy variables to talk about the derivative. I can, if I switch to parametric curves, I can talk about derivatives in terms of parametric curves. So that's very useful just by that formula. That's it. For the second derivative, we use the other formula. So if I'm interested in concavity or anything like that, the second derivative is what I would use. So this is just d dt of dy dx divided by dx dt. So this is going to be d dt of my answer to the previous problem, 3t squared minus 3 over 2t minus 1 over the derivative of x, which is t squared minus t plus 2. So that's it. And now, of course, how do you differentiate the top? Quotient rule, like always. Okay, so it's the bottom times the derivative of the top minus the top times the derivative of the bottom over the bottom squared over 2t minus 1. So this is going to look like in the top, that's 12t squared minus 6t minus 6t squared plus 6 over 2t minus 1 cubed. And so that's 6t squared minus 6t plus 6. Any questions on this or the last one? Did you guys get all that? So once you know the formulas, it's very Calc 1-ish. It's not, the formula is new, but it's not anything crazy new. A lot of your old techniques are applied here, because we're really starting from the basics all over again, just learning how to write curves down and how to find their derivatives. We did that in Calc 1 in the scalar world. Now I'm just showing you how to do it in the parametric world. Arc length. It's another important topic. Okay, so we know how to find the length between 2 points, the distance between 2 points. That's just the distance formula. But if I have this random curve just doing what it do, how do I find out how long it is? What is the length of this curve? Okay, so that is what we're going to talk about next. How to find the length of a curve. So the idea is we're going to take a very calculus approach, and a lot of students don't appreciate this, but I'm just going to tell you and do with it what you will. One of the reasons why calculus is important is not specifically because of all these formulas that you learned, but it's actually a kind of reasoning. And one of the reasons, there are two fundamental sets of reasoning and problem solving that we get from calculus. And one is just the aggregate or the building up of complex things from very simple small things. So in other words, yes, I see a curve here, but I can really think of it as just being a combination of straight lines. But you're like, well, none of the edges are straight. Well, that's where the calculus comes in, because now you think in terms of like Riemann sums and things of that sort, and then your delta x going to 0 and blah, blah, blah. And essentially what a curve is like an infinite combination of straight lines. And so that's what we actually do. To actually figure out the length of a curve, we first envision that it's actually a bunch of straight line segments. And if we find out what it would look like for a finite amount of straight line segments, all we do is let the number of line segments go off to infinity, and we get the curve itself. So you can think of this as going from, say, x1 of t, y1 of t, then this here is x2 of t, y2 of t, right? So I'm thinking of this in the parametric form, x3 of t. And it's not going to be a t, it's going to be of a certain value, t naught, let's say. So let's say this curve is, the curve is x equals x of t, y equals y of t, and t goes between a and b. So for a particular t value, when I plug it in, I'll get a coordinate, just like we saw last time. So this point here is going to be x1, x evaluated at a t value, x of t0, or more specifically, a. Which I can think of that as x of, say, t0, y of t0. This next point is going to be x of t1, y of t1. This is going to be x of t2, y of t2. You know, x of, we'll call this guy tn, because we're going to think of this as n segments, and then we let n go to infinity eventually, which is going to be equivalent to x of b, y of b. So I think of it as that. And so what I can do here is that, notice that the length of the red curve approximates the length of the, I'm going to write black. I know on your screen it looks white, but when I print out the notes, it's going to look black. Okay? And the approximation gets better the more line segments we use. What calculus tells us, this is the calculus concept of the solving the problem, infinite number of line segments will turn the red curve exactly into the black curve. Right, that's a concept that calculus teaches us. It's kind of like how we're like, okay, I want to find the area under a curve. What do? Put a bunch of rectangles under it and measure their area. Okay, how does that help me? Make it an infinite number of rectangles. Now you have the area, right? That's the calculus conceptualization, right? So that's the kind of reasoning that comes from calculus. So that's what we're going to do. So what I'm going to now do is that, well, the length of the, well, that is just like me adding the lengths of things that look like, let me write that out. This is like, so I'm just using the distance formula for each segment. So this is going to be x1 minus x0 squared plus y1 minus y0 squared plus x2 minus x1 squared plus y2 minus y1 squared plus, right? This you can write as just like square root of, let's call the difference in x delta x, I plus delta y, I, and my I is going from 0 to n, right? And so now what we do is the exact length. And I'm not being super detailed here because, again, I am not going to ask you guys to prove this. I'm just going to want you to know where this, have some idea of where the formula comes from. We're pretty much going to take the limit as n approaches infinity of this guy. And to actually get our t variable in there, what we're going to do is we're going to multiply by delta t over delta t and move the bottom delta t under the radical. So this just would become delta x over delta t squared plus delta y over delta t squared, delta t on the outside. And then you'd realize that that's a Riemann sum. And so that means you literally just took an integral from the point A to B, and you end up with delta x over delta t is just the derivative. And delta y over delta t is the derivative. And your delta t just becomes dt under the Riemann sum. Right? So it's like when you had f of xi times delta x, so you take the Riemann, the sum of that, and take the limit, you get the integral of f of x dx, right? Same idea. So that leads us to this equation. So that wasn't in the notes last time, but I decided to just type it up nicely. So yeah, if you want to find the length of a parametric curve, this is how it's done. So of course, there are some things you have to make sure that as you move from A to B, you only go around the curve one time. Parametric curves can have this property where you can actually run back and forth on them. You can think of like even a circle where you can just keep going around the circle. So as long as moving from A to B, you're tracing out a path once, then this formula will actually give you the length from the point XA, YA to XB, YB. Yeah, and again, once you go through this once and you kind of understand it, you never have to worry about it again. At that point, you just memorize this formula. Just another formula to memorize, and you just apply it. And while you're doing your homework, you just write down the formula every time you use it or every time you think about it, and you'll have it memorized before you know it. But that's going to be it. So, for example, here is a parametric curve. X equals e to the t plus e to the minus t. Y equals 5 minus 2t. And I'm looking at t goes from 0 to 3. Now I want to find the length of that curve. That curve is what's depicted here. I want to find out how long it is. Okay, so essentially what we do is we cut it up into a bunch of straight line segments and then let the number of line segments go off to infinity. This ends up creating a Riemann sum, which leads to this formula. So I'll stop here if you guys want to like take a picture or write it down for a little bit. But then I'll just go through and do this. Okay. So here I'm given a parametric curve. By the above, the length of this curve is going to be the integral from 0 to 3 of x prime of t squared plus y prime of t squared dt. So x of t is e to the t. I don't know. Can you guys read that? Let me make this a little bigger. So x is e to the t plus e to the minus t. So if I differentiate that, of course, I'll get e to the t minus e to the minus t. I'm going to square that. And my y is 5 minus 2t. The derivative of that is minus 2. So that's it. Now I'm just going to compute this integral, which at this point, computing integrals shouldn't be too bad. Notice here, so this is going to be, that's 4. Here, I would have e to the 2t minus this times 2 plus e to the minus 2t. The minus 2 plus the 4 is actually a positive 2. I write the positive 2 in the middle to be very suggestive. Does anyone see how I would continue? Hint, compare this to that. Do you see it? No? No. Kendall is mouthing no to me. Notice that this one is actually that. Now do you see it? Yes? No? Maybe so? Kendall, do you see it?
This is probably wrong, but would it just be that with a plus in the middle?
It'd be that with a plus in the middle. So this thing just becomes e to the t plus e to the minus t all squared. So now we have the square root of a square. Technically, that's absolute value. But this here is positive. So we can ignore the absolute values. So this is just integral from 0 to 3 of e to the t plus e to the minus t dt. And it's going to be e to the t minus e to the minus t between 0 and 3. If I plug in 3, I get e cubed minus e to the minus 3. If I plug in 0, I get 1 minus 1. So that's that guy. That's the length of that curve. E cubed minus e to the minus 3 is the length of that blue curve. Arc length. There's another way to look at arc length, the scalar form. I left some examples for you to try on your own. I'm not going to do them because at this point it's just plugging into a formula and doing the integration. But I definitely encourage you to try on your own. I put the answers here. So try that, see if you get it. But for now, what I'm going to do is I'm going to actually derive this formula. So you might not have a parametric curve, but you might be interested in arc length of a scalar curve. And that sort of idea is actually super important in multi 1 and multi 2, because you're going to derive things about surface area and derive things about normal vectors using a formula like this. It turns out that there's a connection between length or size and something like surface area and volume. So this kind of idea this kind of formula you should be aware of in calculus 2. So there was a point where we had like this was the sum of I goes from 0 to n of the length was approximately equal to the square root of delta x squared plus delta y squared. And again, Leibniz notation, very useful. What you can do is you can actually factor out a delta x squared. That just gives you, well, 1 plus dy over dx, delta y over delta x times delta x, because delta x is positive, so the square root of delta x squared is the absolute value of delta x, but delta x is the size of the subintervals, so that's just a positive number, so you can ignore the absolute values. And so now, same old, just take the limit as n approaches infinity of this guy. And that gives you the full length. But now there are no t's to contend with. This just becomes a straight up integral in terms of x's. 1 plus y prime of x squared. Let's put dy dx. dx. Right, so that leads to this formula here. And yeah. So I asked you to find the length of these curves. You're just going to apply that formula. So just need to know these formulas. You don't need to know how to derive them. I'm not going to ask you how to derive them, and I'm pretty sure no one in Calc 3 is going to ask you to derive them either. But you should know them. You should know this is how I find the length of a curve between points A and B, whether the curve is given in scalar form or parametric form. And I'll just mention this now, just throw it out there. Don't need to remember it. But parametric form is equivalent to vector form. So there's going to come a point where you're going to want to think of curves and surfaces in terms of vector functions. And playing around with vector functions is super similar to playing around with parametric functions. It's literally like, it is parametric functions, except you write it in a different notation. So yeah, so another reason why parametric curves are very useful. So yeah, try that on your own. Any questions about any of that? Conceptually, I think it's okay. As always, the devil is in the details. So depending on the problem you get, it just comes down to, do you know how to integrate that thing? Or for dy dx, do you know how to differentiate that thing? Most people don't remember how to differentiate. Integration is a little bit more challenging, but hopefully after the hell I put you guys through with integration in the first half of the semester, you guys can handle almost anything now. So yeah, we're gonna stop there for parametric curves. That's all I want to tell you guys about this. There's more to talk about, but that's all I want to talk about. And that will be enough to move on. Now, I think we have a little less than 10 minutes, so I'm just going to introduce this, but we're not going to get very far. That's okay. We'll pick up with this next time. And I'll leave all the notes again for you guys in case you want to read ahead. Today's the 16th. In case you want to read ahead. One thing I will say is that there's some pretty cool stuff in this section, but we're going to ignore a lot of it because it's unnecessary. It's cool, but it's not necessary. I have taught it in previous Calc 2 classes, so you can find videos of me teaching this stuff, but really you don't need to know it. You can survive without it. These are some topics where it's like, outside of Calc 2, I've never used it. I've never seen anyone use it. It might be worth going through it if you are a physics major, because in physics, polar coordinates, a good understanding of polar coordinates and spherical coordinates is very important. And so the more you know about those coordinate systems, the better. But for the typical person, like you're never going to need to draw a polar curve or do just like stuff in there. So I'd rather move on to stuff that's more useful for the future. And by the way, that's why I skipped another topic that's common in this class, volumes of rotation, like shell and the disk and washer method and things of that sort. Because in multi-1, you're going to learn a new way to do volume where it's like, once you learn that way, that's how you do it forever. Like no one ever uses the shell method outside of Calc 2. And that's across the board. Like, I don't care if you're in physics or whatever. No one's going to find a volume with the shell method. Everyone uses double and triple integrals after a certain point. And it's like in Calc 2, they teach you about the horse and buggy. And you're like, yeah, but everyone drives a car. Like no one is going to, Okay. Anyway, polar coordinates, very cool. It's a different way to look at the world. So I just want to introduce that way so you get your mind kind of starting to wrap around it. It's a cool concept, not super complicated, but it'll take you a while for your brain to switch how it's working. So what I do want to remind you of is what you already know. Normally when we're doing things on like an axis and we're talking about location, we do location in terms of what's called the rectangular coordinate system, right? So what is the rectangular coordinate system? It's basically how you've always dealt with the XY plane. A coordinate system is just a set of rules for how you can travel and locate things in a certain space. We use the rectangular coordinate system ever since you've learned about the XY axis, the Cartesian axis. This was the system you used. Why is it called rectangular? Because you'll notice that you actually form rectangles to figure out locations. So for example, if I wanted to locate the point 1, 5 and the point 3, 1 and the point -2, -3, I would locate this by, well, 1, 5 just means I move 1 unit along the X, 5 units along the Y. Notice that a rectangle is created where the point that is opposite the origin at the corner of that rectangle is the location. Right? So I can locate the point 1, 5 according to the rectangular coordinate system or the Cartesian coordinate system by just creating a rectangle and taking the corner point, the point that's opposite the origin. Okay, nothing new and exciting here, right? But I'm going to want to illustrate similarities next time. Similarly, if I wanted to find the point 3, 1, I know I move 3 units along the X, 1 unit along the Y. From the Y, I move horizontally. From the X, I move vertically. Where these guys meet, again, creates a rectangle. And that's the location. Take the corner of the rectangle opposite the origin. That's my location. What if I wanted to find the point -2, -3? Now, this is very important. I know it's not a big deal in your minds right now, but conceptual is going to be important for later. What you do, how you interpret negative coordinates, is that you actually do a change of direction. Notice that when I was creating my rectangles for the first 2 coordinates, whenever I was doing the X, I moved from the right to the right of the origin. So a +1 in the X coordinate means from the origin, move 1 unit to the right. And for the Y, it was going up. So 1, 5 means I move 1 unit to the right and 5 units up from the origin. And that would be the point 1, 5. When I have -2, -3, how we interpret the negatives is as a change of direction. This is going to be important later. So instead of moving to the right from the origin, -2 means move to the left from the origin. So I'd move left by 2 units. That is called the -2 coordinate. And then I would move down in the Y. So that's -3. So a negative sign in this coordinate system literally means a change of direction. Instead of going right and up, you go left and down. Okay? But again, notice that a rectangle is created. I take the corner that is opposite the origin. That's the rectangular coordinate system. Now, what I want to talk about is the polar coordinate system, which I'll just, in the 5 minutes we have left, I'm going to just describe to you how that coordinate system works. You don't use rectangles, right? So location is defined in a different way here in the polar coordinate system. And here I was just talking about some rectangular coordinate system things, right? So now we want another way to locate points in the plane using circles rather than rectangles. So the idea is, given a point in the plane, so here's my point. Instead of creating a rectangle to get to that point, what I'm going to do is find a circle of radius r where the point lies on its circumference. So this is my point here. What I do is I imagine I could find a circle centered at the origin. Of radius r, center 0, 0, such that that point lies on that circle. Then extend a line from the origin to the point. So here's my point. I found a circle where that guy is on the circumference, and then I extend a line from the origin to that point. Now, the important thing is we are going to let the length of the line be r. That's what it's called, the variable r. And the angle with the positive x-axis be theta. And that leads to this sort of idea. So here's my point. Here is a circle that the point lies on. What I do is I connect it with a line. The length of that line is r, and the angle is theta. Now, whenever I use these two numbers to describe location, I say I'm using polar coordinates. So in the polar coordinate universe, I would actually use a pair called r comma theta. So this is the polar coordinates. So instead of telling me about the rectangle, how far do I move on the x and how far do I move on the y? Instead, what you're going to tell me is how far am I away from the origin and what angle to the positive x-axis am I making? And you can actually achieve a point by the same thing. So given r comma theta, you know I can move at an angle theta, extend from the origin a distance r, and I will hit the point. And just this new formulation is more useful than you'd realize. It's just kind of like parametric equations, where we just do this simple idea of, you know what, let's track the x and the y separately. And a lot of things came out of that. Literally trigonometry came out of that idea. Similarly, once we learn about this new coordinate system, it's going to make a lot of things a lot more convenient than the rectangular coordinate system. There are going to be times where it's useful to think in terms of circles instead of rectangles. And we'll look at some instances of that next time. But that's it. That's basically polar coordinates. We're thinking about location in the plane in a different way. Instead of using rectangles, we use circles. Or equivalently, you can think of it as I'm using a distance from the origin and an angle to determine where I am, versus I'm using, right? So it's kind of like how you can use your location in NYC. You can talk about the street and the avenue, versus another way to talk about the same thing is longitude and latitude. It's two different ways to measure the same thing. So coordinate systems really talk about how do you locate things in a certain space. Rectangular coordinate system is always how we've been doing it up until this point. This is a new way to do that. So it's like longitude and latitude versus street and avenues. It's a different way to talk about location, but it's actually more useful in some situations. Just like how streets and avenues won't work as a locator if you're in the Himalayas on the top of a mountain, right? It's not gonna, there's no streets, right? You have to change the way you locate things to fit the scenario that you're in. So we'll actually stop there. You can read through this and try to figure some of these things out if you want to get ahead, as well as do some of those arc length problems that I left for last time. But for now, just have your mind chew on this for a while. Just, okay, I'm learning to locate things based on angles and distances from the origin. And try to locate this point, like plot where you think that point should be, 1 comma pi over 4. Now, it's very important that you don't think of 1 comma pi over 4 as x and y. It's not. It's r and theta. where would that be? In which quadrant? Etc. So try that for next time. We'll pick up with that on Thursday. Thank you for your time and attention, guys. Once again, I apologize for the late start. I think this is the last time in the semester that's going to happen. So let's actually move forward. So as always, I'll leave the notes. Try to read ahead if you can. And that's it. So you can let me know if you have questions. Remember to fill out the doodle poll for our session on Friday as well as send me questions that you might have, especially going into finals week, things that you're worried about that we can deal with on Friday. And until that, I say we'll stop right there. So have a good night, everyone. Good luck during finals week, and I'll see you in the next one.